Alright, in 7.6 we're going to look at other continuous random variables. So the normal model is just one, and we're going to look at two more that you can see in business applications, and they're called the uniform and the exponential. So the uniform distribution is basically just a rectangle, and the function is 1 over b minus a as long as your variable is in between a and b. And so just as we saw in the normal curve, the probabilities of things happening were the area of the curve. Well, it's pretty easy to calculate areas for this particular curve because they're just areas of rectangles. So the probability that x is between some values c and d is just d minus c over b minus a, and that's really just a ratio of how wide your x variable is. So if d is over here and c is over here, it has this width, and that would be compared to the overall width of the rectangle, and you only have to compare widths because the height is a constant. And then our expected value is just basically the center of this rectangle, which would be a plus b over 2 right in the middle here. And our variance is the width of this thing squared divided by 12, and then our standard deviation is the square root of that. Okay, let's look at an example. We arrive at a bus stop and want to model how long you'll wait for the next bus. So the sign says that buses arrive at about every 20 minutes. So you assume the arrival is equally likely to be anywhere in the next 20 minutes. And that equally likely assumption right there is what gives us this constant height. So what we say is there's a 1 in 20 chance that the bus will arrive between 0 and 20. So again, from our previous slide, b is 20, a is 0. So 0 minutes from now the bus will arrive, 20 minutes from now the bus will arrive, and you can see it here. Then we break it into increments, whatever increments you want. We did 5 here, and basically the probability at any given time is 0.05, and basically this probability increases as we move from left to right. So if we're at 19 minutes, if we've been waiting for 19 minutes, that'd be 19 times 0.05, or there's a 95% chance that a bus will arrive within that time frame. So it's pretty much exactly the same kind of methods to calculate probabilities that we did with the normal curve, but in the normal curve we had to look up these areas under the curve because it has a very unique bell shape. In this, you don't have to look up anything because we can easily calculate the area of a curve of a uniform distribution like this because it's just a rectangle. So we look, if we arrive at a bus stop and want to model how long we'll have to wait, so 20 minutes, and so we would expect to wait 10 minutes. So how do we get that? It's exactly the middle of this uniform distribution. So we expect to wait 10, and with a standard deviation of, so just plugging into those equations we had before where b is 20, a is 0, we would have a standard deviation of 5.77 minutes. Let's just do one more example. What's the probability we wait less than 5 minutes? So that would just be this from 0 to 5, and that'd be 5 times the height of 0.05, which would give us 0.25, so there's a 25% chance we'll wait between 0 and 5 minutes. That's how you would look at this. Okay, that's it for the uniform. Oh, I should also mention uniform is very common in lotteries. So in lotteries you have the digits 0 through 9. There's 10 digits there. You want them each equally likely because you don't want, let's say, 5s to show up more frequently than 9s, because then people would catch on to that and they would start playing more 5s in the lotto. So you want those numbers to show up about the same number of times. So if you do a curve based on lottery numbers and how frequently they show up, it will look very similar to this. The next one we'll look at is the exponential distribution, and it is a function based on the equation lambda times e, this is your exponential key on your calculator, raised to the minus lambda x, and our x has to be greater than 0, and so does our lambda. And so again we'll get kind of an interesting curve here, and we'll see how we can calculate things. So to find the probability between any two values, s and t, as long as s is less than t, we will just take e raised to the negative lambda times s minus e raised to the negative lambda times t. And there is some math that goes into why you do it that way, but that's beyond the scope of this class. So we would basically just want to plug and chug as long as we know the time intervals. And so again, this one's kind of common for how things will occur in time. So we'll look at an example here. If we have a website experiences 4 hits per minute, what is the probability that we'll have to wait less than 20 seconds, 1/3 of a minute, between 2 hits? So basically we convert the 20 seconds to minutes, since our lambda is 4 hits per minute. And so we say, what's the probability of x being between 0 and 1/3? And we just use our formula that we had before. So it was e to the minus lambda s. Lambda is our expected value, which is 4 hits. So it'd be 4 hits times our s, which is our left endpoint. So it's 4 times 0. Minus 4, which is lambda, again, our expected number of hits in 1 minute, times the right endpoint, which is 1/3 of a minute. And so we subtract these out, and we get this just goes to 1, so this becomes 1 minus this, and basically we have a 73.6% chance that we'll wait 20 seconds or less between hits. And that's pretty much it for 7.6. We will use uniform distribution certainly more in the class. The exponential we won't. I think we'll use it again, but we certainly don't use it as much as the normal curve. We'll use that a lot, or the uniform distribution.